Hi everyone. Now we are going to discuss a single phase full wave AC voltage controller with RL load. So here this is a circuit diagram which is showing a resistance and inductance which are connected in series to form the load. And the supply voltage is Vs and the two thyristors T1 and T2 are connected in anti-parallel. Source current is Is, I0 is the load current. So here we will be marking, this is the source voltage and here we are marking the load current and your source current. Since it's a series connected circuit, the current flow for the source current and I0 both will be the same because there are two thyristors which are conducting at an instant of time. Now, the thyristor T1 is forward biased at angle 0 to pi. Now I can trigger on the thyristor T1 at any instant of time, and this Ig1 is indicating the firing angle given to the thyristor 1. So when I am trying to fire the thyristor at an angle alpha measured from the 0, then the entire source voltage will be appearing across the load voltage. So therefore, I will draw the output voltage. So here I will be drawing the output voltage like this from alpha to pi. So during that instant of time, what happens is that the current I0 flows in the system. And this Is is flowing through T1 through I0, and therefore Is and I0 are the same. Now, since the load is an inductive load, the current will be lagging behind the voltage. And therefore, the current gradually increases. And when it reaches pi, the voltage has come to 0 and starts reverse biasing. So here it is going in the negative direction. Therefore, I can say that T1 is getting reverse biased, but the current is still flowing in the thyristor T1 because the current is lagging behind the voltage. So the current has not gone below the halting current, and therefore it will start in the conduction mode. So it will be start continuing its conduction till an angle beta. So this angle is beta. This angle is beta. So therefore, a reverse voltage will be appearing across the load like this. And once it reaches beta, the current has come to 0. It's already in the reverse biased condition, and therefore T1 will remain in the off state. Now, T1 has gone to the commutation mode at an angle beta. So it's only the conduction is from alpha to beta, it starts conducting. Now, the next thyristor T2 is fired at an angle pi plus alpha, that is at this instant of time. So the next firing will happen only at this instant, which is indicating the value of pi plus alpha. So from beta to pi plus alpha, none of the thyristors are conducting, and therefore I can say that the load voltage is 0 because no thyristors are conducting. And since no thyristors are conducting, the current is also 0. Now at pi plus alpha, the thyristor T2 is fired, and therefore the entire source voltage will be appearing across the load like this. So it will be conducting from pi plus alpha to 2 pi. Now we will look at the current, the source current and the load current. Now the thyristor T2 is conducting in this direction. So therefore the current is moving in the opposite direction of the conventional current what we have already marked, and therefore the current will be going like this. And when the voltage is 0, your current is not 0 because it's a lagging, and it will still continue to conduct until the current reaches 0 at the extinction angle. So that time your load voltage will be the source voltage. And from this particular point to this particular point, no thyristors are conducting, and therefore the load voltage will be 0. Current is also 0. And after that, again at this instant, thyristor T1 is again triggered. And it will be continuing like this. So from the point 0 also I can complete the waveform like this. So therefore, I can also mark the conduction angle gamma like this. So that is the gamma. This is beta and this is alpha. Now we need to draw the voltage across thyristor. So for the thyristor, we can see that T1 is conducting from alpha to pi plus alpha. So during that time, the on-state voltage drop is coming across the thyristor T1. When the thyristor is in the off state, that is the thyristor is fired at an angle alpha, but there was a negative voltage which was coming across this thyristor T1 during this instant, that is till this period, till the current is 0, and that was because of the conducting thyristor T2. That is because of the conducting thyristor T2. Just observe it from here. So this is being replicated over here, which was for the thyristor T2. So that voltage in reverse with the opposite polarity is coming across the thyristor T1. Or else I can say that T2's voltage drop, the voltage across the conducting thyristor T2 during this instant of time is coming with opposite polarity across the thyristor T1 for this instant. So like this. And at this particular period of time, the thyristor has stopped conducting, and therefore none of the thyristors are conducting during this period of time, and therefore whatever be the source voltage will be appearing across the thyristor T1. Like this. And again, during this instant of time, none of the thyristors are conducting, so whatever be the source voltage will be appearing across the thyristor. And thyristor T1 is conducting during this period, T2 is conducting during this period. T2 is conducting during this period. So that time, whatever be the voltage drop across T2 will be appearing across the T1. And since they are oppositely connected, a negative voltage will be coming across the thyristor like this. And again, when it is not conducting, it will be like this and continuing. So in the similar fashion, you can also draw the waveform for thyristor T2. So this is how the entire waveform explanation for a AC voltage control with RL load happens. So this is just indicating the entire waveforms taken from the textbook. So you have your source voltage, the thiring of the thyristors T1 and T2. Then this is your source current and the load current, load voltage, thyristor voltage T1 and thyristor voltage T2. So this is for alpha greater than phi, where phi is nothing but the power factor. So that is the displacement by which the voltage and the current is shifting. Now we will also see the waveform for what happens when the alpha is less than the angle phi. Now let us concentrate on this waveform. This waveform is a discontinuous waveform, and here you can see that the thyristor T1 is conducting from alpha to alpha plus gamma, which is nothing but your angle beta, the extinction angle. And then the thyristor T1 is remaining off from alpha plus gamma to pi plus alpha. Now just imagine that I am able to reduce my angle alpha. When I am trying to reduce my angle alpha, what happens is that the conduction angle the gamma starts increasing, because gamma is nothing but beta minus alpha. So when I am trying to reduce your alpha, your gamma starts increasing. When this gamma is approaching the angle pi, we will see what will happen. So that is, during that time, when gamma is approaching to pi, then I can say that the thyristor T1 will be conducting from alpha to pi plus alpha. Rather than conducting from alpha plus gamma, it will be conducting to pi plus alpha. Then thyristor T2 will be conducting again from pi plus alpha to 2 pi plus alpha. So under such conditions, the current will not be zero like this, and the voltage will not be having a drop like this. So you will be getting a more continuous waveform. Now we will also see the value of alpha when gamma equal to pi. So that condition normally arises depending upon the value of your phase angle, because the phase angle phi is depending upon the type of the load. So under the steady state condition, the load current will be a sine wave and lagging behind the voltage by an angle phi, because the current is nothing but a continuous current, because I have reduced my angle alpha. So what happens is that the current has come to a continuous value, and the source voltage V0 is also continuous. There is no drops, because all the thyristors are conducting at an instant of time. So basically, under such conditions, voltage control is not possible. So the reduction of alpha below the phase angle phi will not result in a voltage control in the case of a RL load. So the AC output power can be controlled only for alpha greater than your phase angle phi. So when angle alpha is being reduced, and when the conduction angle gamma reaches to a value pi, there is a continuous conduction, and the only thing what happens is that the source voltage and the load voltage will be the same, and source current and the load current will be the same, and there will be only a displacement of phi. So basically there is no voltage control which is happening in the system. So therefore I can say that in the case of phase controlled AC voltage controllers, the value of firing angle should be phi less than alpha less than 180 degree. So from this figure you can also derive the output voltage V0 RMS, which I will not be deriving it here because just substitution. It is from alpha to beta, and the time period is 1 by pi Vm square sin square omega t d omega t. Thank you.